The reading material, the Nielsen textbook. And let me show you. This is how it looks like. It's the cover page. It's going to be posted to the Google Classroom for you to use this textbook as a support material for your studies. But today, we're going to investigate some of the properties of graphs and functions. As soon as in grade 11, you already got familiar with many of the functions, such as trigonometric functions, main trigonometric ratios, primary trigonometric ratios. Then it was the quadratic functions that you learned in grade 11. Also, you know the root function, you know the exponential functions from grade 11. And it's going to be useful for us to get familiar with new material. Today we're going to start with not so complicated topic in our program. Today we're going to discuss properties of these graphs in particular. Remember, in previous course, you learned how to sketch these graphs. You learned how to solve equations with those functions. But in reality, the functions of greater degree are going to have some more interesting characteristics for us to discover. And these characteristics, these properties of these functions can be used by you while analyzing them and while solving problems. So let's take a look at this paragraph. It's page 17, paragraph 1.3. And here we can see a list of trigonometric, exponential, quadratic, module functions. And first and most important criteria for any function is the interval of increase and decrease. You must be familiar with this criteria as soon as when we sketch the parabola for quadratic function. You know that 1/2 of the parabola is going to be decreasing, and this one is going down, decreasing, and this one is going up, which means it's increasing. Basically, what increasing means. In interval of increase, it's such an interval which within a function domain where the y value of the function get larger moving from left to right. So as we change x value moving from left to right, you see y value is increasing as we go from left to right. You see, it means the function is increasing. On the other hand, we can see that as we move from left to right here, the y value of the function are getting lower, right? That's how we identify intervals of increase and decrease. In basic notation, it could be stated as if f(x1) less than f(x2), function from x1 less than function from x2, then this interval is increasing. If the sign of an equality the other way around, f(x1) greater than f(x2), it means function is decreasing. Okay, so what are x1 and x2? x1 is the value to the left and x2 is the value to the right. So as soon as we're moving from left to right. Okay, any questions about that? Any questions? No questions for Anna. Okay. So moving on, basically why we're doing it. We're doing this to answer the question, which criteria could the student use to differentiate between these different types of functions? One of them we already discovered, it's intervals of increase and decrease. For each function has its specific intervals of increase and decrease, and we should be able to identify those. Next criteria that we have to be familiar with is whether this function odd or even function. These two types of functions are different in terms of their end behavior. What is an end behavior? You see this little arrow on this graph here and there? This is the point that describes the end behavior of the graph. In this particular case, this is a polynomial function of third degree. You see, quadratic function had only one vertex like this. But the third degree, which is an odd function, it has basically two vertices, one here, one there. And these vertices basically change the direction of the function. You see here, we're increasing, then we're decreasing, then we're increasing again. And what is interesting about this function? That on the end behavior, you see here and there, this function travels to the left-hand side, to the negative infinity in y-axis, and the right-hand side to the positive infinity in y-axis. So it means if we take somehow large x value, this function would take such a big value that we can assume it's somewhere near infinity. And what is specific about that function? Any function that has rotational symmetry about the origin, this is exactly what we can see here. It's a symmetry around the origin. Algebraically, all odd functions have the property that f of minus x equals minus f of x. So basically, if you apply minus to the independent variable, you can extract this minus outside of the function and solve it as a normal function, and you're still going to get the right answer. But what are we interested in? When you have an odd function, your end behavior is always going to be like that. Negative infinity on one side and positive infinity on the other side. While for quadratic function, for parabola, which is an even function, you can see that end behavior is both same for both ends of the function, whether it's looking up or down. Here it goes to positive infinity. This scenario, when parabola upside down, it goes to negative infinity, and both end behaviors are this. And on the other hand, even function, they don't share such property as the odd function, where if you substitute minus x into the function, you're going to get this function with minus. For even function, if you substitute minus x, you're going to get f of x, because these functions are symmetrical over the y-axis. You see, if you take x value from left, minus x, and you take the x value from right, plus x, you're going to get the same result, because this even functions are symmetrical over the x-axis. Here you can see an example of fourth degree polynomial function, and you see, now we can see some kind of relationship here, right? Third degree is an odd function. Second and fourth degree are even function. And now we already can make a criteria to identify whether this function is odd or even. This is a really important material. So you know that parabola has a equation y equals x squared, right? Do you agree with me? No question about it. Parabola looks like this. Of course, we can add x, subtract some constant value c, but it wouldn't make a crucial difference into the shape of the curve that we have, because in all scenarios, it's going to be a parabola, right? Now, this exponent, the greatest exponent in our equation, is the degree of a function. X squared is or even function of second degree. If you would have y equals x to the third power, this function would have third degree, right? Even if you have plus x squared, plus x, plus c, still, you only look at the greatest exponent. If the greatest exponent is 3, then it's third degree function. And function with the third degree would be an odd function. Now we can make a statement that all even exponents are giving us even function, y equals x to the power n, where n equals numbers 2, 4, 6, 8, and so on. This is going to be an even function. And guys, I insist that you use your copybooks and you write down these definitions with me, okay? Okay, Rana? Okay, Ahmad? Guys, please, let's join the activity together. Let's work together. Ask the questions. I don't trust that you don't have any questions, so please do that. Now, second scenario, y equals x to the power k. Let's k and then just some notations that we choose. And k numbers would be such as 1, 3, 5, 7, and so on. These are odd degree functions. And make a sketch next to each one of them. So you see even functions have an end behavior same on both ends, and odd functions have an end behavior opposite on both ends. As well as you have to write this property of even and odd degree function, that f of minus x equals negative f of x for odd degree, and for even degree, f of minus x equals f of x. Please write down this to notation. Let me know once you finish. Okay, did you finish copying it down? Guys, please turn on your cameras. Ahmad, oh, you have a mic? Great. Guys, I'm talking to you. Are you with me? Please turn on your camera, Ahmad. And keep it on. I know you have a camera. I'm waiting, guys. Why, Rana? What's the problem? I just want to let you know, if you're aiming for a good mark at the end of the course, you have to participate in a class activity. You have to show that you're working with everybody else in the class. You have to show your attendance, because all of that is considered while issuing the final mark. And unfortunately, I have some students that they never talk in the class, they never ask questions, they never solve problems with me together, and at the end of the course they come and say, I'm not satisfied with my mark. But how can I help a student if he never showed any effort to get this good mark? He never showed his participation in the class. I cannot give a mark out of the thin air, just so you know. But today, okay, it's the first class. We're just starting. So let's move on. So we described two important criteria, such as intervals of increase and decrease, whether the function or even. And now we have to talk about continuous function and discontinuity. There is such a thing as discontinuity in the function. For example, on this graph, this is, I believe this is function, just give me a second. This is an exponential function, and you can clearly see on this drawing that in the middle of this graph, right here, there is no values for x. So basically, all values on this x line are basically absent from the solution or from the domain of the function, right? Domain is the x-axis. So domain has a discontinuity at this point. Let's say this point would be 1, x equals 1. Then we would say that domain of our function equals x, e, r, all rational numbers, but interval would be from negative infinity to 1, not included, and the second interval from 1 to positive infinity. So at point 1, we would have a discontinuity in this function, basically. And you can see that this function has positive infinity on this end and negative infinity on this end. So as our function approaches this vertical asymptote, that's how we call this type of discontinuities. This is a vertical asymptote. As our function approaches this vertical asymptote, it tends to travel to infinity. Depending on the characteristics of your function, to the left-hand side, it could travel to positive infinity, and to the negative infinity from right-hand side. Or, as you can see in this example, left-hand side travels to negative infinity, and right-hand side travels to positive infinity. This is an example of discontinuity, basically a break in the graph of a function. It's called a point of discontinuity. And continuous functions. Continuous functions are such that any function that doesn't contain any holes or breaks over its entire domain. This is standard odd degree function. Third degree function is going to be continuous function. So what do we know up to now? We know that the function could increase and decrease. We know that the function could be odd or even. And we know that function could be continuous and discontinuous at this moment. Let's look at example number 1, just to clarify that you understand main criteria of functions. Match each parent function card with a characteristic of its graph. Each card may only be used for one parent function. We have function f of x equals x, f of x equals 2x, f of x equals modulo x, and f of x equals sine x. And here we have 4 cards. Range of y greater than 0, domain xer, so all rational numbers, infinite number of zeros, and as x travels to negative infinity, y travels to 0. So let's start with the first one. Range for y greater or equals to 0. This function should not have any values below the x-axis, because y should be only positive. Looking at all of these functions, I see that f of x equals x definitely does not comply with this property. F of x equals 2 of x does not comply with this property, even though it looks like y values are only positive. It does not comply with it because we never could get y equals 0. Meanwhile, here in the range, you can see that y equals 0 is included. So it's not f of x equals 2 to the power x, but the modulo function f of x equals x, so it could be equal to 0, and it could never be negative. So first card goes here. Great. Now second one, domain xer. So let's take a look at it. So domain xer, all rational numbers. So for f of x equals x, yeah, this card suits this function f of x equals x, because we can use any x value. Our range, our domain of this function is infinite. Let's take a look. Maybe we can use it somewhere else. F of x equals 2x. Okay, and basically here, I would say that here we also can implement this card, but remember, we can use it only once. And this card also fits the third one. So let's keep it for now because we can use it only once. Infinite number of zeros. Infinite number of zeros is the property of the periodic function. And we know that trigonometric prime or trigonometric ratios, they are periodic functions. And you can see that sine x, in fact, has infinite number of zeros, right? Because it will cross the x-axis again and again and again and again, all the way up to infinity. So it has an infinite number of zeros or solutions. So I say that card number 3 goes to this card, this function. So now, okay, we have only 2 functions left to describe. As x travels to negative infinity, y travels to 0. I can see that f of x equals x definitely not giving me this result, because as I travel x to the negative infinity, it gives me y travels to the negative infinity as well, right? Because f of x equals x basically means y equals x. Okay, so there is only one function left, and this card is going to fit this graph, because you can see here, I'll zoom in a little bit. You can see how this curve behaves. As you travel x to the negative infinity, so you take x, really big number here, you're gonna see that your y value gonna become something like 0.00000 and many zeros. Basically traveling to 0, but never actually equals to 0. That's the reason why we couldn't use the first card for the second graph. So x travels to negative infinity, y travels to 0. So now I can say that second card, domain XER, is suitable for first graph. Right now, I just show you some basic methods of analyzing the graphs in order to put some properties with respect to those graphs. And you should be able to do the same stuff just by looking at the graph and on the form of the function. You should be able to identify key features of this graphs. You can see, you can check my answers here. This we will skip, non-essential. Let's write down the key summary of what we learned today. Function can be categorized based on their graphical characteristics, domain and range, x-intercept and y-intercept, continuity and discontinuity, intervals of increase and decrease, symmetry, whether we have symmetry over the origin or the y-axis. Remember, odd functions are symmetrical over the origin, and even functions are symmetrical over the y-axis. And at the very end, we look at the end behavior, whether the function travels to positive infinity or negative infinity on ends of its range. What do you need to know is that the given a set of graphical characteristics, the type of function that has these characteristics can be determined by eliminating those that do not have these characteristics. Some characteristics are more helpful than others when determining the type of function. So from this part, you're going to have a home assignment. There's going to be a first home assignment. So you're going to take 7, 8, and 9. These 3 questions. just to enhance your understanding of the topic. I strongly insist that you do your home assignment on a regular basis, on a daily basis, because only through practicing you can get confidence in your test, in your assignments, in mathematics in general. And just by keeping that in mind, you won't struggle so much with these questions. So it's page 24. And we'll move on directly to the sketching graph of function. Meanwhile, it is important to understand key characteristics of the function. We also have to understand how to sketch those graphs. In the previous year, in the grade 11, you learned the general form of your functions, that the function could be expressed as y equals AF brackets k times x minus d brackets are closing plus c. And you have to remember well that each of these parameters or variables in our general form has special information for us. For example, c value is going to be displacement in y-axis, y-axis translation, let's call it like that. Meanwhile, d would be responsible for x-axis translation. Then we have k factor, and this factor k is responsible for let me remember, for horizontal compression. Let's say horizontal stretch. Horizontal stretch, and A is responsible for vertical compression. What it basically means, let me show you in an example. So let's say I have a sine function like this. It is convenient because it's like a string, right? Imagine if we have this string right here, and imagine we can manipulate it. So what C, let me sketch the coordinate axis right here. Something like that. So I have y-axis and I have x-axis. So what coefficient C does to my function? Coefficient C translates my entire graph in y-axis. So for example, if C is positive, it means my function is translated some amount of units upwards, like this, in y-axis. Because basically each point of this graph is going to be translated upwards. Then, or if C is negative, it's going to be translated downwards. Then D stays for x-axis translation. If D positive, then we translate our function to the right. If D negative, we move to the left. I can note it like this: minus D to the left plus D to the right, minus C down plus C up. And this is it about translations and about stretches. So horizontal stretch is basically something that happens when I grab my function and I pull it. You see, it's getting stretched, it's getting wider. This is my horizontal stretch. You see, my function became wider. This is what K factor responsible for. And finally, factor A responsible for vertical compression. And vertical compression you can imagine as when something like this happens to my function. You see, it's getting compressed. It's getting compressed like this. You see, it's getting less stretched in the y-axis. Or on the other hand, it could become more stretched in y-axis and become something like this. Become wider in y-axis. Is that clear? I hope I refreshed your memory, because this is what you're supposed to learn in grade 11. Now moving on, let's see the different examples of transformations that had been made to parent function. Here we can see a quadratic function that been translated 3 units upwards, C coefficient, 1 unit to the right. How to identify this? You just look at the vertex of quadratic function. You join vertex of the parent function and transformed function like this. And you can see that we have been translated 3 units upwards and only 1 unit to the right. 1 here and 3 here. So this is translation that has been done to our function. Now, horizontal stretch is 0.5. So basically all the points of our parent function has been factored by 0.5. You can see the function became a little wider in y-axis, so it got stretched out. And 2f, sorry, 2, coefficient 2 here, basically made our function stretch upwards a little bit more. But it's hard to see it because we also stretched it horizontally, right? So it's not so visible here. Moving on to exponential function, 2 to the power x. And again, you can see translation 3 units up, translation 3 units to the right, compression, stretch and compression. Same thing happened to all of the other functions. Take a moment to screenshot it for your future references. Okay. And here we're coming to an interesting, important criteria of any function, which is a turning point. As you know, for quadratic function, we have only one turning point, is the vertex, right? Where a function changes its direction. But as we increase the degree of the function, the turning point may change. For example, the turning point on a curve where the function changes from increasing to decreasing, or vice versa. For example, A and B are turning points on the following curve. You see, it's odd degree function, third degree, and we have 2 turning points. One more thing to write down is the general equation of transformed function. This is what I showed you at the very beginning. Please take a moment to copy it down and remember what each of these parameters are describing. Here you can see in this example that parameters K and A are related to stretches, compressions, and reflections, while the parameters D and C are related to translations. Since division and multiplication must be performed before addition, all stretches, compressions, and reflections must be applied before any translations, due to the order of operations, basically. So let's take a look at how it's done. We have a parent function square root of x and stretch function y equals 3 of x. And how is this stretch applied to our points? Basically, vertical stretch is going to be a multiple of the y coordinate of each of the points of the parent function. Let's say we have square root of x, we found 4 points, and to apply stretch to this function, we're going to multiply y coordinate of each one of these points by factor of 3. Vertical stretch, the graph by factor of 3 occurs when all the y coordinates on the graph of the parent function are multiplied by 3. Next step, after you apply the stretches, all stretches that you have, in this particular example, we have only one, is multiple of 3. After you did that, only then you apply your transformations. Only then you apply your translations. And translations are applied pretty much the same way. If you have C constant, which is responsible for translation in y-axis, you simply substitute this number from y coordinate. And that's how you find the points of your transformed function. Translating the graph 2 units down occurs when 2 is subtracted from all the y coordinates on the graph of the stretch function. Here you can see a result of such transformations. And since the domain of both the parent function and transform function is the same, that's really important to remember, the interval of the increase is also the same. The difference occurs in the range. The y values of the transform function increase faster than the y values of the parent function, because we applied vertical stretch, right? Factor of 3. Factor of 3 basically gave us this vertical stretch. You see, when you're working with trigonometric functions, the approach is pretty much the same. But for example, here, you have to see that factor that is giving us a horizontal compression basically should be applied as an inverse multiple. So if we multiply by 3 in the function, if we multiply x by 3, we have to divide by 3 the x coordinates, okay? Apply a horizontal compression by factor of 1 over 3 and the vertical stretch by factor of 2. On the graph, f of x equals cosine x. Multiply the x coordinates by 1 over 3 and the y coordinates by 2. So trigonometric functions and regular functions are no different in this term. And in terms of translations, if you see you have multiple in front of the function, which is a, then you see this coefficient in front of x, which is k. So you multiply each point y by 2 and each x point by 1 over 3. You get the new set of points, which you can then use to create your graph. And here you can see an example what happened to this curve. First of all, it got compressed in x-axis. You see this, basically this wave maximums became closer to each other, and it got stretched in y-axis like so. because you see maximum value is now greater than it used to be before. I hope it's clear on how to work with the transformations of points. Here it is important to notice that after we made a vertical stretch, our function changed its range. Remember, sine function or cosine, sine and cosine functions, they have their own limited range. And if for the parent function of cosine was from -1 to 1 range, after stretching it in y-axis, we got -2 to 2 range. So basically multiply the range by 2. Reasoning about order of transformation is not much to talk about here. Most importantly, first you apply stretches and compressions, then you apply translations. This is what I want you to remember. Compressions, stretches, then finally you're applying translations. Let's take a look at the example number 4. Reasoning about the order of transformations. Describe the order in which you would apply the transformations defined by y equals -2 f of 3x plus 1 minus 4 to f of x equals square root of x. Then state the impact of the transformations on the domain, range, intervals of increase, decrease, and then behavior of the transform function. Let's review this example real quick. So first of all, remember, we apply compressions and stretches. Here I can see that x-axis has a compression with factor 3 and stretch in y-axis with factor -2. So I multiply all of my x coordinates by 1 over 3, and I multiply all of my y coordinates by -2. Set of points that I'm going to give would be 0, 0, 1 over 3, -2, 4 over 3, -4, and 3, -6. Since multiplication must be done before addition, apply horizontal compression by factor of 1 over 3, a vertical stretch by factor of 2, and reflection in the x-axis. To do this, multiply the x-coordinate of points of the parent function by 1 over 3 and y-coordinate by -2. This is an important step, guys. What happened here that our function basically our function got mirrored over y-axis because we multiplied by negative number. So that's what caused the function to get mirrored. Basically mirrored in x-axis, reflected in x-axis. Here we already have our points, including stretches and compressions. And final transform form would include translation, right? We have translation of 1 unit to the left. Remember, in the initial function, we have x minus d. So if we have +1, it means d is negative. So it means the function is translated to the left in x-axis and translated downwards in x-axis, in y-axis, subtract 4. We simply subtract 1 and 4 from x and y coordinates respectively. you get the final set of points. And after applying all translations, translate the graph of f of x, 1 unit to the left and 4 units down. To do this, subtract 1 from x coordinate and 4 from y coordinates of points on the previous function. The transformed function is now a decreasing function on the interval -1 to infinity. You see, the parent function was positively increasing function. But now, as we reflected this function over the x-axis, you see, now it's facing downwards, and the function is decreasing, and the interval is different now. Now the interval is -1 to positive infinity. We have to plot the points of the final transform function, the horizontal translation, change the domain from xer, x greater than or equals to 0, to x greater or equals to -1. So basically, because we translated our function 1 unit to the left, our range is increasing. Our range of the function increased. The reflection in the x-axis and the vertical translation changed the range from yer, y greater or equals to 0, to yer, y less or equals to -4. So basically, x-axis reflection happened here. And the summary of what we learned today is as follows. The key ideas: transformations on a function y equals a of a times f of k times x minus d plus c must be performed in a particular order. Horizontal and vertical stretches compressions, including any reflections, if applicable, must be performed before translations. All points on the graph of the parent function y equals f of x are changed as follows. X, y coordinate is going to be divided by k factor, and we're going to plus d to it, and y is multiplied by factor a, and we add c to it. Please, this is very important. This is very important stuff to say for the future. When using transformations to graph, you can apply a and k together, and then c and d together to get the desired graph in the fewest numbers of steps. What do you need to know? First of all, the value of the determines whether there is a vertical stretch or compression or reflection in the x-axis. As we've seen today, if coefficient a is greater than 1 by modulo, then the graph of this function is stretched vertically by factor a. On the other hand, if a is a factor, so it's something divided by something and it's less than 1, like 1 over 2, the graph is compressed vertically by factor a. When a less than 0, the graph is also reflected in x-axis. That's really important to remember. Those are 3 characteristics of factor a. The value of k determines whether there is a horizontal stretch or compression or reflection in the y-axis. When k greater than 1, the graph is compressed horizontally by the factor 1 over k, but when k is a fraction, the graph is stretched horizontally by factor 1 over k. When k is less than 0, the graph is also reflected in y-axis. So you see, when a less than 0, we're reflecting in x-axis. When k less than 0, we're reflecting in y-axis. And also, it is important to see that when k is factor, basically what's happening, the graph is getting stretched. If k is not a factor, graph is getting compressed in y-axis or horizontally.